Right now, as you rest, something vast is occurring. Two titans are moving through the darkness of space, drawn together by invisible forces spanning billions of years. Our home, the Milky Way galaxy, is on a collision course with our nearest large galactic neighbor, Andromeda. The dance has already begun. This cosmic encounter will unfold over timeframes almost impossible for human minds to truly comprehend. Billions of stars, including our sun, will be swept into new orbits. Night skies will transform beyond recognition. Yet despite its scale, this collision represents not an ending, but a transformation. A celestial waltz of almost unimaginable beauty. Tonight, we'll journey through this future together. The science of galactic collisions reveals something profound about our universe. That even in apparent destruction, new forms of creation emerge. That time flows differently at cosmic scales. As your thoughts drift tonight, we invite you to contemplate these immense timeframes, to find comfort in the knowledge that even galaxies are in constant motion. That change is the only true constant. Our story begins with you, here, now. A conscious observer of the cosmos nestled on a small planet, contemplating events that will unfold long after our brief human moment has passed. In 4 billion years, our galaxy will begin merging with Andromeda. The collision itself will span hundreds of millions of years, moving at speeds of around 402,000 kilometers per hour toward one another. Yet despite this velocity, the distances are so vast that the process unfolds with surprising gentleness. Individual stars rarely collide. Mostly, they simply find new orbital paths within the merged system. The collision will create waves of new star formation as gas clouds compress, lighting the newly formed galaxy with the birth of countless stellar systems. It's a cosmic renaissance of creation. Tonight, we'll explore what astronomers and physicists have discovered about this future event, how they measured the motion of a galaxy 2.5 million light-years away, and determined our cosmic fate. We'll journey through the mechanics of galactic mergers, the evidence captured by our most powerful telescopes, and the computer simulations that reveal what awaits our descendants. This documentary offers no cause for alarm, only wonder at processes unfolding across timescales far beyond a human lifetime, an invitation to perspective. The stars you see through your window tonight are moving. The galaxies they form are moving. Everything in our universe is in constant, graceful motion. Nothing truly stands still. We'll examine what will happen to our solar system during this merger, whether Earth will survive, and what new night skies might look like for any beings witnessing these events. Scientists have mapped the future with remarkable precision, revealing the stages of this cosmic collision. From initial approach to final merger, this knowledge emerges from the same physics that governs objects here on Earth. Gravity works consistently across all scales, from falling apples to interacting galaxies. Our journey tonight will span from the earliest observations of Andromeda, through the discovery of its motion toward us, to the latest simulations of our galactic futures. The night sky has always inspired human imagination, from ancient myths to modern astrophysics. Our story connects these timeless wonderings with cutting-edge science. As you rest, imagine timeframes so vast that mountains rise and fall like waves, continents drift and merge, and galaxies themselves interact like slow-motion dancers. The collision of our Milky Way with Andromeda will create not destruction, but birth, a new galaxy astronomers have already named Milkomeda, or sometimes Milkomeda. Chapter 2: Premise and Human Meaning. Why should this distant future event matter to us now? What meaning can we find in cosmic changes scheduled long after humanity as we know it has likely evolved into forms we cannot predict? The answer lies partly in perspective, in understanding our place within time, in finding comfort within vastness rather than fear. When we contemplate events billions of years in the future, something shifts in our consciousness. Our daily concerns, while still important, reveal themselves as part of a much larger context. This cosmic perspective doesn't diminish human experience. Rather, it enriches it, placing our brief moment in the flowing river of time. The collision of galaxies reminds us that even the most seemingly permanent structures in our universe are temporary. That change occurs at every scale, from quantum fluctuations to galactic transformations. Consider this: the atoms in your body were forged in ancient stars. You are, quite literally, made of stardust. And that cosmic material will continue its journey long after our individual lives. There's something deeply comforting about this continuity, about being part of processes that extend far beyond our personal timelines, connected to both cosmic past and future. The Milky Way Andromeda collision also teaches us about the nature of apparent catastrophes. What seems like destruction often creates conditions for new forms of emergence. When galaxies collide, star formation accelerates. New stellar nurseries form in the compressed gas clouds. Life potentially gains more opportunities to emerge on newly formed planets. Astronomers studying these processes aren't motivated by fear, but by curiosity, by the human desire to understand processes unfolding across timescales far beyond our brief lives. The universe doesn't operate on human timescales. And in this truth lies freedom. Freedom from the anxiety of immediacy, and an invitation to consider ourselves part of something beautifully, almost unimaginably vast. The night sky above you contains light that has traveled for millions of years. When you observe Andromeda, you're seeing it as it was 2.5 million years ago. Light that left when our earliest human ancestors walked Earth. This connection between past, present, and future creates a kind of cosmic symmetry. We observe ancient light while contemplating future mergers, standing at a unique moment between what was and what will be. For many, this cosmic perspective brings not existential dread, but its opposite. A sense of being part of something magnificent and ongoing, connected to cycles of creation that transcend individual existence. Our human meaning isn't diminished by cosmic scales, it's contextualized within them. Our capacity to understand these processes is itself remarkable. The fact that conscious beings evolved who can contemplate events billions of years in the future is extraordinary. We are the universe becoming aware of itself, pondering its own future. This perspective offers a different relationship with time itself, beyond the ticking of clocks and urgency of schedules, toward something more expansive and generous. Contemplating galactic mergers reminds us that change is not something to fear. That transformation is woven into the fabric of existence. At every scale and across all timeframes, ancient philosophers advised contemplating the stars to gain wisdom. Modern astronomy gives us specific knowledge about those stars. Together, they offer both information and perspective. The Milky Way Andromeda collision will unfold with a kind of cosmic patience. Stars and planets moving through their celestial choreography. Timeframes that encourage contemplative awareness rather than anxiety. When we understand that even galaxies merge and transform, our own changes and transitions can be seen in a new light, as natural processes rather than disruptions, as evolution rather than ending. This cosmic perspective doesn't solve our immediate human challenges, but it does place them within a larger context, one that has consoled thinkers across cultures and centuries. Astronomers who study these future events aren't motivated by practical concerns. They won't affect tomorrow's weather or next year's crops. Yet this knowledge enriches our understanding of existence. There's something profoundly humbling about mapping events that no human will ever witness, about extending our minds beyond our biological limitations, about transcending our brief moment through understanding. As you rest tonight, consider that the very space around our planet is in motion, that we're all traveling together through the cosmos, participants in an ongoing journey of transformation. The night sky above you will gradually change over centuries and millennia, stars shifting position relative to one another, constellations slowly transforming their ancient patterns. The galactic collision reminds us that everything we consider permanent is actually in flux. Mountains rise and erode. Continents drift. Galaxies merge and form anew. This knowledge doesn't need to create existential distress. Instead, it can foster a sense of cosmic belonging, a recognition of our place within these grand, ongoing processes. As we'll discover, our solar system will likely survive this collision intact. Carried to a new position in the merged galaxy, possibly with more spectacular night skies than we currently enjoy. Chapter 3. Origins and Early Science. The story of our understanding begins not with telescopes, but with human eyes and curious minds. Looking upward at the night sky, wondering about those misty patches of light. Ancient observers across cultures noted a faint cloud-like object in the constellation Andromeda, visible even without instruments on dark, clear nights. The earliest recorded observation comes from 964 CE by Persian astronomer Al-Zufi. In his book of fixed stars, Al-Zufi described this object as a little cloud. He couldn't have known he was observing an entire galaxy containing roughly 1 trillion stars, a cosmic city of suns. For centuries, this luminous patch remained a mystery, too distant to resolve into individual stars with early instruments, its true nature hidden beyond human understanding. The telescope's invention in the early 1600s began to change our view. In 1612, German astronomer Simon Marius provided the first telescopic observation of Andromeda, describing it as a flame seen through horn. Still, its true identity remained elusive. Was it a nebula within our own galaxy, a distant star-forming region, or something else entirely? Charles Messier, the famous 18th century comet hunter, cataloged it as M31, the 31st entry in his list of fuzzy objects that might confuse comet searchers, not understanding its true significance. The great debate about these nebulae continued into the early 20th century. Were they within our Milky Way or entirely separate island universes? The question represented a profound shift in our cosmic understanding. The answer came in 1923, when astronomer Edwin Hubble identified individual stars within Andromeda using the 100-inch Hooker telescope. Among them were Cepheid variables, stars whose pulsation rates reveal their true brightness. Hubble's measurements proved Andromeda lay far beyond our galaxy, at least 900,000 light-years away, later refined to 2.5 million. Our universe suddenly expanded from a single galaxy to many. The cosmic perspective had fundamentally changed. This discovery transformed our understanding of the cosmos. The universe was vastly larger than previously imagined, populated with countless galaxies like our own, each containing billions of stars. But Hubble's work was just the beginning. The next question emerged naturally. Were these distant galaxies moving? If so, in what directions? And what might this tell us about the universe's future? The answers would come through spectroscopy, analyzing the light from distant objects. By examining how galaxy light shifts toward red or blue wavelengths, astronomers could determine if objects were moving away or toward us. This technique relies on the Doppler effect, the same phenomenon that causes a passing ambulance siren to change pitch. When objects move away, their light stretches to longer, redder wavelengths. When approaching, it compresses to shorter, bluer wavelengths. Most galaxies showed redshifts, indicating they were moving away from us. This led to Hubble's second great discovery, the expansion of the universe. But Andromeda was different. Andromeda's light showed a blue shift, evidence it was moving toward our galaxy. But this discovery's full implications weren't immediately understood. The collision course wasn't yet clear. Early measurements suggested Andromeda was approaching at around 300 kilometers per second. But determining whether a collision would occur required more precise data, understanding the sideways motion, not just the direct approach. For decades, this question remained unanswered. The technology to measure the tiny sideways motion of a galaxy 2.5 million light-years away didn't exist. The collision remained theoretical. Scientists worked with the tools available, refining their understanding of both galaxies, mapping their structures and compositions, building increasingly sophisticated models of galactic interactions. The Milky Way revealed itself as a barred spiral galaxy spanning about 100,000 light-years, containing between 100 to 400 billion stars, with a supermassive black hole at its center. Andromeda emerged as a larger spiral, spanning approximately 220,000 light-years, containing approximately 1 trillion stars, also harboring a central supermassive black hole. Computer simulations of galaxy collisions advanced through the late 20th century, revealing the complex dynamics of these cosmic encounters. The beautiful, chaotic dance of interacting gravitational fields. These simulations showed that galactic collisions were not the cataclysmic events once imagined. The vast spaces between stars meant direct stellar collisions were extraordinarily rare. Instead, stars would be swept into new orbits. By the 1990s, astronomers had developed increasingly sophisticated models, but a crucial question remained unanswered. Would the Milky Way and Andromeda definitively collide, or might they pass near each other? The answer would require measuring Andromeda's sideways motion with unprecedented precision, a technical challenge requiring the most advanced astronomical instruments and patient observations over many years. Through each discovery, our understanding of cosmic processes deepened. The universe revealed itself not as static and unchanging, but as dynamic and evolving across vast timeframes. The most profound realization was that galaxies themselves have lifespans. They're born, evolve, interact, and transform, just as stars do. The seemingly permanent night sky is actually in constant, majestic motion. Chapter 4. First evidence and scale. The definitive answer about our galactic future came in 2012. A team led by astronomer Roland van der Merel used NASA's Hubble Space Telescope to make unprecedented measurements. For the first time, astronomers precisely tracked the sideways motion of Andromeda, not just its approach velocity, revealing the complete trajectory of our neighboring galaxy. This required measuring changes smaller than 1/10,000th of a degree, tracking subtle shifts in position over years of observation. Technological precision that would have seemed magical to earlier astronomers. The results were conclusive. The Milky Way and Andromeda are on a direct collision course. In approximately 4.5 billion years, the first encounter will begin. A cosmic certainty written in the motion of stars. To understand the scale of this future event, we must first comprehend the distances involved. And this requires moving through orders of magnitude that challenge human imagination. Let's begin with our familiar home planet, Earth, a sphere approximately 12,742 kilometers in diameter, circling our Sun at an average distance of about 150 million kilometers. Our Sun is merely one star among hundreds of billions in the Milky Way, orbiting the galactic center at a distance of roughly 28,000 light-years. 1 light-year equals about 9.5 trillion kilometers. The Milky Way itself spans approximately 100,000 light-years from edge to edge, a vast spiral of stars, gas, and dust, rotating once every 225 to 250 million years. Andromeda lies approximately 2.5 million light-years from us. The light we see tonight left that galaxy when our early human ancestors were just beginning to use stone tools. A connection across both space and time. If the Milky Way were shrunk to the size of a dinner plate, Andromeda would be another plate about 25 meters away. Yet despite this vast distance, the gravitational attraction between these cosmic titans is enough to draw them inexorably together. The evidence for collision comes from multiple converging lines of investigation. Spectroscopic measurements showing Andromeda's approach velocity. Proper motion studies revealing its sideways movement. computer simulations projecting future trajectories. The precision of these measurements is remarkable. We can determine that Andromeda is moving toward the Milky Way at approximately 110 kilometers per second, with a sideways motion of just 17 kilometers per second. From these measurements, astronomers calculate the first encounter will occur in about 4.5 billion years. The complete merger process will take an additional 2 billion years, resulting in a new, larger elliptical galaxy. To put these timeframes in context, our Sun is currently about 4.6 billion years old. Earth formed shortly after. Life emerged on our planet within the first billion years. By the time the galactic merger begins, our Sun will have aged into a red giant, expanding to perhaps engulf Mercury and Venus, rendering Earth's surface uninhabitable due to increased solar radiation. This cosmic timing means that human beings in our current form will not witness this galactic collision. Either our species will have evolved into something different, or we will have spread to other star systems. But what if we could witness this merger? What would we see? Computer simulations give us remarkably detailed predictions. A cosmic dance unfolding over hundreds of millions of years. The first approach will bring Andromeda looming larger in our night sky, growing from a faint smudge visible only on clear nights to a vast spiral structure dominating our view. As the galaxies make their first pass, gravitational forces will distort both systems, drawing out long tidal tails of stars and gas, creating magnificent bridges of stellar material between the two. The night sky would gradually transform. New constellations would form. Stars from Andromeda would mix with our familiar patterns, creating spectacles of unprecedented beauty. The galactic disks would pass through each other like ghosts. Individual stars rarely colliding due to the immense distances between them. But gas clouds would interact, compress, and trigger waves of new star formation. The collision would continue through multiple passes, each gravitational interaction more complex than the last, gradually transforming both spiral structures into a single merged system. The final result, according to simulations, will be an elliptical galaxy, lacking the elegant spiral arms of its predecessors, but containing the combined stellar populations of both. What about our solar system? What fate awaits our cosmic neighborhood? Surprisingly, the odds favor survival. The vast spaces between stars make direct collisions extremely improbable. More likely, our solar system will be swept into a new orbit, perhaps closer to the center of the merged galaxy, perhaps farther out in its halo, but likely remaining intact as a unit. The view from Earth, if it still exists, and if anyone remains to see it, would be transformed. The night sky would blaze with many more visible stars. The merged galactic core would shine with the light of billions of suns. The most profound aspect of this collision is that despite its cosmic violence, represents not an ending, but a transformation, the birth of a new galaxy, sometimes called Milkomeda, with characteristics unlike either of its predecessors. But the Andromeda Milky Way merger is not the final chapter in our cosmic story. Our local group contains dozens of smaller galaxies, many of which will eventually join this merged system. Looking even further ahead, astronomers predict this combined galaxy will eventually merge with the Triangulum Galaxy and potentially other members of our local group, creating an ever larger cosmic structure. As we've journeyed from Earth to the scales of galactic interaction, we've traversed distances that defy intuitive understanding, from kilometers to millions of light years, from human timescales to billions of years. But this is just the beginning of our exploration. In the next part of our journey, we'll examine the physics of these interactions in greater detail and what observations of other colliding galaxies tell us about our future. Chapter 5: Contradictions and Anomalies. As confident as astronomers are about the coming collision, some fascinating contradictions have emerged in recent research. Questions that complicate our understanding of this cosmic encounter. Anomalies that invite deeper investigation. One of the most intriguing challenges comes from measurements of dark matter. That mysterious substance comprising roughly 85% of all matter in the universe. Invisible to our telescopes, yet detectable through its gravitational effects. Both the Milky Way and Andromeda are embedded within massive dark matter halos. These invisible structures extend far beyond the visible disks of both galaxies and significantly influence their gravitational interactions. Some models suggest these dark matter halos will begin interacting long before the visible galaxies meet, creating subtle distortions in both systems, potentially altering their collision trajectory in ways difficult to predict. Since we cannot directly observe dark matter, its exact distribution remains uncertain. Different models produce slightly different collision timelines, some suggesting the merger might begin hundreds of millions of years earlier or later than expected. Another complication emerges from recent measurements of Andromeda's mass. Studies published in 2018 suggested its total mass might be similar to the Milky Way's, rather than significantly larger as previously believed. This finding challenges earlier models of the collision. If the galaxies have comparable masses, their interaction becomes more equal. Less like a larger galaxy absorbing a smaller one, more like true peers merging. The Hubble constant, the rate of universe expansion, also introduces uncertainty. Different measurement methods yield slightly different values, and these variations affect predictions of galactic motion over billion-year timeframes. The collision itself is certain, but its exact choreography remains open to revision. Science thrives on these uncertainties. They aren't weaknesses, but opportunities for deeper understanding, reminding us that even cosmic certainties contain nuance. The local group's overall dynamics present another puzzle. Our galactic neighborhood contains over 54 galaxies moving in complex relation to one another. Their combined gravitational influences create a cosmic web of interactions. Recent observations suggest the Large Magellanic Cloud, a satellite galaxy of the Milky Way, contains more mass than previously thought. Its gravitational pull might slightly alter our galaxy's trajectory, adding another variable to collision predictions. The intergalactic medium gas and dust between galaxies presents another complicating factor. As the galaxies move through this medium, they experience a subtle but cumulative drag effect, potentially altering their paths over billion-year timescales. Some astronomers have proposed that the Milky Way's spiral structure might not be as stable as once thought. Our galaxy's spiral arms might be transient features, forming and dissolving over hundreds of millions of years. If true, this would mean the Milky Way Andromeda will encounter might look different from our current galaxy, its spiral structure potentially altered, its stellar distribution already changed by internal processes. Competing computer simulations offer different visions of the collision process. Some suggest a direct hit is most likely. Others propose more glancing encounters before the final merger. Each scenario produces different outcomes. The uncertainties extend to the final form of the merged galaxy. While most models predict an elliptical galaxy, some suggest a peculiar type of lenticular structure. The exact morphology depends on angular momentum conservation during collision. Our Sun's location during this process is another area of debate. Some simulations show it being thrown into an extended orbit far from the galactic center. Others suggest it might migrate inward. The difference depends on subtle initial conditions. The collision might trigger the formation of a quasar-like active galactic nucleus, as gas funnels toward the merging supermassive black holes, potentially creating one of the most energetic phenomena in the universe. However, competing models suggest both galaxies may have insufficient gas by that time. Star formation will have consumed much of the available material, potentially resulting in a dry merger with limited new stellar birth. Recent observations of other colliding galaxies reveal surprising diversity in outcomes. The antennae galaxies demonstrate dramatic tidal tails and intense star formation, while other mergers proceed more quietly with less spectacular effects. Which path will our galactic merger follow? The answer depends on factors still being researched, including the precise angle of approach, relative velocities, and gas content of both galaxies. Even the fate of the supermassive black holes at each galactic center remains uncertain. They will eventually merge, but the timeframe and process are debated. Some models suggest they may orbit each other for billions of years before uniting. This orbiting phase could produce gravitational wave ripples in space-time itself, potentially detectable by future, more sensitive instruments, offering a way to observe the final stages of black hole merger. The most remarkable aspect of these scientific uncertainties is that they exist despite studying objects containing trillions of stars. Even with this complexity, astronomers can predict the general outcome with confidence, while remaining humble about the details. The anomalies and contradictions don't undermine the central finding. The Milky Way and Andromeda will merge, but they reveal the beautiful complexity inherent in cosmic processes. As measurement technologies improve, some of these questions will find answers. New space telescopes will provide more precise data. Advanced computer simulations will integrate more variables. Yet some uncertainty will always remain. A reminder of the limitations of prediction across cosmic timescales, and the inherent complexity of systems containing billions of interacting elements. This scientific humility is not weakness, but strength. It acknowledges the boundaries of current knowledge, while continuing to refine and improve our understanding. The questions themselves reveal how far astronomy has advanced. From wondering what Andromeda was, to debating subtle details of its future interaction with our galaxy. These contradictions and anomalies invite continued investigation, each representing not a failure of understanding, but an opportunity for deeper insight. As you contemplate these cosmic puzzles, consider how they mirror the uncertainties in all prediction. The future, even of galaxies, contains possibilities rather than certainties. A reminder to hold predictions lightly. The collision itself represents both an ending and a beginning. The conclusion of two separate galactic histories, and the dawn of a new, combined cosmic story. Perhaps most fascinating is how these uncertainties echo ancient philosophical questions about determinism versus probability, about whether the future is fixed or fluid. Modern astronomy suggests a middle path where large-scale outcomes follow predictable patterns, while specific details remain open to variation. Chapter 6. Myths, Misreads, and Edge Cases. As with any topic spanning cosmic scales and timeframes, the Milky Way Andromeda collision has accumulated its share of misconceptions. Popular myths that distort scientific understanding, and edge cases that, while fascinating, can mislead. Perhaps the most persistent myth involves catastrophic destruction. Images of stars violently smashing together, planets being torn from their orbits. A vision of cosmic apocalypse. In reality, galaxies are mostly empty space. The average distance between stars is so vast that direct collisions are extraordinarily rare. If our sun were a ping-pong ball, the nearest star would be hundreds of kilometers away. This scale means galaxies pass through each other like ghosts. Individual stars almost never collide. The interaction is gravitational rather than physical, a dance of orbits rather than impacts. Dramatic visualizations sometimes contribute to these misconceptions. Computer simulations often compress billions of years into seconds, creating the impression of violent, rapid change rather than gradual transition. Another common myth suggests Earth faces imminent danger, that the collision represents a threat to our planet. This misreading compresses vast timeframes into human scales of concern. The reality offers perspective. By the time Andromeda arrives, our sun will have already evolved into its red giant phase. Earth's oceans will have long since evaporated. Our planet's surface will likely be uninhabitable for complex life. This timeline places the collision beyond the scope of immediate human concern, a cosmic event unfolding on timescales so vast that our species will either have become unrecognizably different or have spread beyond this solar system. The collision teaches us to distinguish between human and cosmic timescales. Events that seem catastrophic when compressed into minutes actually unfold with such gradual patience that they represent transformation rather than destruction. Some popular accounts suggest the collision will create spectacular night skies immediately, that we might witness Andromeda growing larger in our lifetimes. This misunderstands the timescales involved. Andromeda's apparent size in our sky changes imperceptibly over human lifespans. Even over thousands of years, the difference would be barely measurable. The spectacular views lie billions of years in the future. Another misconception involves the uniqueness of this event. That galaxy collisions are rare cosmic catastrophes. In fact, they are common throughout the universe. A normal aspect of galactic evolution. Astronomers have observed thousands of interacting and merging galaxies, systems in various stages of collision. From initial approach to final coalescence, our future merger is not exceptional, but typical. Some accounts suggest the collision might disrupt the solar system's stability, sending planets into chaotic orbits or ejecting worlds into interstellar space. This overestimates the local gravitational effects. The gravitational interaction occurs primarily between the galaxies as whole systems. Individual solar systems are affected mainly through gradual changes in their galactic orbits, not through disruption of their internal dynamics. Our solar system will likely maintain its integrity throughout the merger. The planets will continue orbiting the Sun, while the entire system adopts a new path through the merged galaxy. Edge cases do exist where solar systems could experience closer encounters with passing stars. These might perturb the orbits of distant objects like comets, but such events would be rare exceptions rather than the rule. Some artistic depictions show the collision as instantaneous, a moment of cosmic impact, rather than a process unfolding over hundreds of millions of years. This compresses timescales beyond recognition. The actual merger will proceed so gradually that any hypothetical observers would perceive only subtle changes during their lifetimes. Stars shifting position slightly, new structures emerging over generations. A cosmic patience beyond human experience. If humans could somehow witness the entire collision at its natural pace, would unfold with such majestic slowness that it would appear more like the gradual changing of seasons than a catastrophic event cosmic change at its most serene. Another misreading involves the certainty of prediction. Some popular accounts present the collision timeline as absolutely fixed, when in fact it contains significant uncertainty margins. Current estimates place the first encounter about 4.5 billion years from now, but this carries uncertainty of several hundred million years, a reminder of the limits of prediction across such vast time frames. Some discussions mistakenly describe the merger as Andromeda consuming the Milky Way, implying one galaxy will survive while the other is destroyed. This misunderstands the nature of galactic interactions. The process is more accurately described as a mutual transformation. Neither galaxy will survive in its current form. Both will contribute to the structure and composition of the newly formed system. Popular science sometimes overstates the role of central black holes, suggesting they drive the collision process. While they do influence the final stages of merger, the interaction primarily involves the galaxy's overall mass distributions. The supermassive black holes at each galactic center, while enormous by stellar standards, comprise only a tiny fraction of each galaxy's total mass. Their merger represents a dramatic finale rather than the main event. Some accounts imagine Earth experiencing a dramatically different sky overnight, stars suddenly appearing brighter or in new positions. This misunderstands both the timescales and physics involved. Any changes would unfold over millions of years, gradual shifts in stellar positions and brightnesses. Not sudden rearrangements, but slow, elegant transitions. Cosmic patience beyond human experience. Visualization limitations sometimes create misconceptions. Computer simulations typically represent galaxies with far fewer points of light than actual stars, creating the impression of less complex systems. In reality, each galaxy contains hundreds of billions of stars, moving in intricate orbital patterns, creating merger dynamics far more complex than simplified models might suggest. Some discussions incorrectly suggest the collision could be averted through hypothetical technology or cosmic intervention. This vastly underestimates the energies involved. The combined momentum of trillions of stars moving through space, guided by gravitational forces operating across millions of light years, represents energies beyond any conceivable technological manipulation. The most profound misunderstanding may be viewing the collision as something to fear rather than to contemplate with wonder it represents. Not cosmic violence, but cosmic patience. Not an ending, but a transformation. Not a catastrophe, but an evolution. The edge cases and myths surrounding galactic collisions reveal something important about human perception. Our tendency to compress vast timescales into human frames of reference, and to imagine cosmic processes in terms of human experiences. In reality, galactic collisions unfold with a dignity and patience beyond our direct experience. Neither rushed nor violent when viewed at appropriate scales, but graceful and inevitable expressions of gravitational choreography. Chapter 7: Stakes and What Changes If True. What truly changes if our understanding of the Milky Way Andromeda collision is accurate? What are the stakes of this cosmic knowledge? And how does it alter our relationship with time, space, and our place in the universe? The immediate scientific stakes involve our understanding of galaxy evolution, how these massive stellar cities form, interact, and transform. The collision provides a future case study in our own cosmic backyard. By studying this predicted merger alongside observations of other colliding galaxies, astronomers can refine models of galactic evolution, connecting past, present, and future in a continuous narrative of cosmic development. The collision also presents a natural experiment in extreme astrophysics. What happens when supermassive black holes merge? How do star formation rates change during galactic interactions? Questions addressable through this future event. For astronomical navigation, the collision represents a fundamental transformation. The familiar celestial landmarks used for thousands of years will gradually shift. New patterns will emerge as stars adopt different positions. This change reminds us that even the seemingly fixed stars are in motion, that constellations are temporary configurations, and that cosmic permanence exists only in timescales too brief to reveal the underlying flow. For measurement and modeling, the collision challenges our computational capabilities. Simulating the interaction of trillions of stars across billions of years requires mathematical models of extraordinary sophistication. These models stretch the boundaries of prediction itself, revealing both the power and limitations of scientific forecasting. What can be known with confidence versus what remains probabilistic? Perhaps the most profound stake is philosophical. The collision reveals that even the largest structures we know, galaxies containing hundreds of billions of stars, are themselves temporary arrangements in an ever-evolving cosmos. For telescope development, the coming collision provides motivation for increasingly precise measurements. Each new generation of instruments reveals more details, refining our understanding of the approaching merger. The James Webb Space Telescope and its successors will capture ever more detailed views of interacting galaxies, providing glimpses of processes similar to what awaits our own system, a preview of our galactic future. For timescale comprehension, the collision offers a framework for understanding deep time. The billions of years before encounter represent a span longer than Earth's entire evolutionary history, a perspective that humbles human timeframes. This vastness of time provides both comfort and context, removing any sense of urgency or threat, while placing human existence within the flowing river of cosmic evolution. The stakes extend to our understanding of habitability. how galactic environments influence the development of life. Would the merged galaxy be more or less conducive to biological emergence? Some research suggests galactic mergers can trigger waves of new star formation, creating fresh generations of planets, potentially expanding opportunities for life to emerge in new solar systems. Conversely, the active galactic nucleus formed during merger might increase radiation in central regions, creating environments less suitable for fragile biology. A cosmic rearrangement of habitable zones for human descendants, should they still exist in recognizable form. The collision would present both challenges and opportunities. Navigation systems would require adjustment. Stellar neighborhoods would transform. Any advanced civilization existing billions of years hence might witness the early stages of collision, perhaps even developing technologies to utilize the changing gravitational landscape, surfing the waves of cosmic restructuring, while the collision itself unfolds across billions of years. The knowledge of this future event changes something in us now. It extends our mental timeframes beyond the immediate, inviting a perspective that transcends our brief individual lives. What changes most profoundly is our relationship with permanence itself. The understanding that even galaxies, the largest coherent structures we directly observe, are themselves transient arrangements in cosmic history. This recognition shifts something in human consciousness, from seeing the universe as a fixed backdrop to human affairs, to understanding it as a dynamic process unfolding across multiple timescales. The stakes include our conception of cosmic identity. Will future beings identify with Milkomeda rather than separate galaxies? How might consciousness evolve alongside these vast cosmic transformations? For cosmic cartography, the merger represents a fundamental redrawing of our local universe. The familiar structure of the local group will change, as its two largest members combine into a single dominant system. This cartographic shift mirrors earlier revolutions in our understanding, from Earth-centered to Sun-centered models. From seeing the Milky Way as the entire universe to recognizing it as one galaxy among billions. Each shift expands our cosmic context, places us within ever larger frameworks of understanding, and reveals the provisional nature of all cosmic configurations. For stellar life cycles, the collision introduces new variables. Some stars might form that would otherwise never exist. Others might evolve differently within altered galactic environments, a cosmic reshuffling of stellar destinies. The merger might trigger bursts of star formation as gas clouds collide and compress, creating new generations of stars and planets. Cosmic nurseries born from the gravitational interaction. For planetary systems, including our own, the stakes involve new orbital trajectories. Our Sun will likely be swept into a different path through the merged galaxy, potentially providing different stellar neighborhoods to traverse. This movement wouldn't threaten planetary orbits around the Sun, but would change the Sun's journey through galactic space, altering the distant stellar scenery visible from Earth or its descendants. The most beautiful implication may be that the atoms in your body forged in ancient stars will continue their cosmic journey through this merger and beyond. The material elements of your being will witness this grand transformation even if your consciousness does not. The stakes extend to our understanding of dark matter. The collision will reshape the dark matter halos surrounding both galaxies, potentially revealing new insights about this mysterious substance. As these invisible halos interact, their effects on visible matter might become more pronounced, offering observational windows into dark matter dynamics, a cosmic laboratory for studying the unseen. For theories of gravity, the collision provides a test case of unprecedented scale. Will the galaxies behave exactly as our models predict? Or will subtle discrepancies reveal new aspects of gravitational physics? Such questions highlight how the collision serves scientific understanding, not merely as a future event to contemplate, but as a natural experiment testing fundamental theories. Perhaps the deepest stakes involve meaning and perspective. How does knowing the future fate of our galaxy change our relationship with the cosmos? What philosophical insights emerge from this knowledge? The collision reminds us that we exist within flowing processes rather than fixed structures. That change characterizes the universe at every scale, from quantum fluctuations to galactic transformations. This recognition doesn't diminish the significance of human experience, but places it within an expanded context, connecting our brief moment to processes spanning billions of years. As we contemplate what changes if our understanding is accurate, we discover that the most profound transformation may be in consciousness itself. In how we perceive our place within cosmic time, the approaching merger invites a dual awareness of both our brief human moment and the vast processes within which it unfolds. It's a perspective spanning orders of magnitude in both space and time. What changes most fundamentally is the story we tell about the cosmos, from static backdrop to dynamic narrative, from fixed stage to flowing river, from permanence to transformation. This narrative shift might seem subtle, but it represents a profound reorientation, from seeing ourselves within a completed universe to recognizing our place within an unfolding cosmic story. What lies ahead in this story? Beyond the merger itself, the combined galaxy will continue its journey, perhaps eventually merging with other members of the local group, in an ongoing process of galactic evolution. But even this expanded timescale represents just a chapter in cosmic history, as the universe continues its expansion, as new structures form and dissolve across billions and trillions of years. A story still unfolding. Chapter 8. Strongest competing theories as we approach the culmination of our cosmic journey. Let's examine the strongest competing theories about the Milky Way Andromeda collision, each supported by substantial evidence, each offering a different vision of our galactic future. The standard merger theory represents the scientific consensus. It envisions a complete merger occurring over approximately 6 billion years, resulting in an elliptical galaxy containing the stars of both predecessors. This theory builds on observations of other galactic collisions, computer simulations incorporating gravitational interactions, and measurements of Andromeda's trajectory toward the Milky Way. The evidence includes Hubble Space Telescope measurements confirming Andromeda's approach, observations of similar mergers throughout the universe, and our understanding of galactic dynamics over long timescales. Under this model, the first close approach occurs in about 4.5 billion years. The galaxies pass through each other, then reverse direction, making several passes before finally merging. The resulting elliptical galaxy would lack the distinctive spiral structure of its predecessors. Its stars would move in more randomized orbits, creating a more spherical or football-shaped stellar distribution. This transformation from spiral to elliptical mirrors a pattern seen throughout the universe, where galactic collisions often convert spiral galaxies into ellipticals. A cosmic evolution of galactic morphology. The standard merger theory suggests not destruction, but transformation. Our galaxies won't be destroyed, but reborn in a new form. Their stars rearranged into a massive elliptical galaxy that would appear as a bright, extended object in any distant observer's telescope. A competing perspective emerges in the modified collision theory, which suggests a more complex interaction influenced by dark matter dynamics and the larger context of the local group. This theory proposes that the dark matter halos surrounding both galaxies will interact first, creating tidal effects that alter the collision's trajectory, potentially resulting in multiple close approaches before merger. Under this model, the first interaction might occur earlier than in standard predictions, perhaps in 3.5 to 4 billion years rather than 4.5 billion, due to the extended reach of dark matter halos. The evidence includes computer simulations incorporating dark matter distributions, observations of warping in galactic disks caused by gravitational interaction, and measurements suggesting earlier than expected tidal effects. This theory predicts a more prolonged merger process, with more dramatic tidal tails and stellar bridges between galaxies, and potentially greater disruption to both galaxy structures. The resulting galaxy might not be a standard elliptical, but could retain some disk-like characteristics, a hybrid morphology reflecting the complex interaction history. This perspective emphasizes the role of invisible components in galactic evolution, how dark matter shapes the visible universe, and the limitations of models based solely on observable matter. A third framework, the extended timeline theory, proposes a significantly longer merger process, perhaps spanning 8 to 10 billion years rather than 6, with more orbital interactions before final coalescence. This theory suggests the Sun might complete its red giant phase before the merger concludes, potentially evolving into a white dwarf during the collision process. Witnessing the cosmic dance from multiple evolutionary stages, evidence includes recent refinements in mass estimates for both galaxies, suggesting slightly different orbital dynamics and a more extended interaction timeframe. This perspective emphasizes cosmic patience even beyond standard models, a galactic dance unfolding across timeframes that make even geological epochs seem momentary. A truly deep time perspective. These competing theories don't contradict the fundamental reality of the coming collision, but offer different choreographies for this cosmic dance, variations on timing, tensity, and outcome that remind us how science continually refines its understanding. Each theory carries implications for our cosmic neighborhood, how other local group galaxies might be affected, whether smaller satellite galaxies will join the merger or be ejected. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, might be incorporated into the merged system, or potentially flung into more distant orbits by gravitational interactions. Similarly, the Triangulum Galaxy M33, currently approaching Andromeda, might participate in a more complex multiple galaxy merger, creating an even larger galactic system. What all these theories share is the certainty of interaction, the inevitability of galactic transformation, and the understanding that our current cosmic configuration is temporary. They differ primarily in timescales and details, not in the fundamental outcome. A cosmic variation on a theme rather than contradictory visions. This scientific consensus with variation represents the strength of modern astronomy. Agreement on fundamentals with healthy debate about specifics. A balance of confidence and continued inquiry. As we contemplate these competing theories, we're reminded that science progresses through refinement. Each new observation and calculation adding detail to our understanding, an ever-sharpening picture of cosmic processes. The theories converge on transformation rather than destruction, on cosmic evolution rather than ending, on the emergence of new structures from the merger of old. This convergence offers a profound reminder about change itself, that even at galactic scales, transformation follows patterns. That cosmic processes, while vast, are not chaotic, but choreographed. What we're witnessing through these competing models is science in action, not a weakness of understanding, but its strength. A community of minds refining a vision of events billions of years hence. Chapter 9. New Science. Instruments and paradoxes. Our understanding of the coming galactic merger continues to evolve alongside astronomical technology. New instruments and methods reveal previously hidden details, resolving some paradoxes while uncovering others. The James Webb Space Telescope, with its unprecedented infrared sensitivity, allows astronomers to peer through cosmic dust, revealing stellar nurseries and galactic structures in extraordinary detail. This capability transforms our study of other merging galaxies, providing clearer views of star formation triggered by collisions, and offering previews of processes that await the Milky Way and Andromeda. Webb's observations of gas distributions in interacting galaxies reveal complex flows and compressions, showing how collisions create ideal conditions for new star formation. These observations confirm some aspects of merger models while challenging others. The rates of star formation sometimes exceed predictions, suggesting our own galactic collision might be even more productive than expected. Meanwhile, the European Extremely Large Telescope ELT, with its 39-meter primary mirror, will provide unprecedented resolution of distant galaxies, including those in various stages of interaction. These new super telescopes offer us not prediction, but observation. They can watch hundreds of galaxy collisions. Already in progress across the universe, each one a frame in the cosmic film that shows what awaits our own galactic neighborhood. This observational power allows astronomers to create more refined models, moving from general principles to specific case studies. A catalog of cosmic collisions informing our understanding of our own future. Another frontier emerges in gravitational wave astronomy. Instruments like LIGO and Virgo detect ripples in spacetime, created when massive objects merge or interact, while current detectors focus on black hole and neutron star mergers. Future generations might detect signals from interacting galaxies, offering a new sensory channel for understanding cosmic collisions. The planned Laser Interferometer Space Antenna, LISA, will detect lower-frequency gravitational waves, including those from supermassive black hole interactions, potentially revealing the fate of galactic centers during mergers. This multi-messenger astronomy, combining light, gravitational waves, and other signals, creates a more complete picture of cosmic processes, resolving paradoxes through complementary data. One such paradox involves the fate of central black holes during galactic mergers. How and when do they eventually combine? What happens during their orbital dance? Recent simulations suggest the supermassive black holes might maintain separate orbits for billions of years, creating a binary system at the heart of the newly formed galaxy, before eventually merging in a burst of gravitational radiation. This final merger would emit more energy than all the stars in the observable universe, though primarily in gravitational waves rather than light. A cosmic event of unimaginable power. Neutrino astronomy offers another emerging window into galactic processes. These ghost-like particles pass through most matter, but carry information about the most energetic cosmic events. Future neutrino observatories might detect signals from active galactic nuclei formed during mergers, providing insights into the extreme physics of these environments. Adding another layer to our understanding, the most profound aspect of these new instruments is how they extend human perception beyond our biological limits, allowing us to see gravity itself through waves in spacetime, or to detect ghostly neutrinos carrying messages from cosmic cataclysms. These technological advances help resolve the paradox of prediction across cosmic timescales. How can we forecast events billions of years hence? By observing similar events already unfolding throughout the universe. Each interacting galaxy pair becomes a natural experiment, a data point in understanding our own future. Collisions frozen at different stages of a process spanning billions of years. Computer modeling capabilities advance alongside observational technologies. Today's simulations incorporate trillions of calculations, modeling the gravitational dance of billions of stars with unprecedented precision. These models reveal emergent behaviors in galactic systems, properties that arise from countless interactions, creating patterns predictable at large scales despite chaotic local dynamics. This balance between chaos and order presents another cosmic paradox. How systems composed of essentially random stellar motions create the ordered structures we observe as galaxies. The answer emerges through gravitational self-organization. How simple attractive forces operating across vast distances create complex but patterned structures over time. This principle applies to both current galactic structures and future mergers. Order emerging from apparent chaos, pattern from randomness, one of nature's recurring themes. New research also explores the paradox of galactic identity through time. In what sense will the Milky Way survive this merger? When does one galaxy become another? This question mirrors the ancient philosophical puzzle of the ship of Theseus. If every component is gradually replaced, at what point is it no longer the same object? A paradox of identity across transformation. Applied to galaxies, this becomes even more complex. As stars maintain individual identities while their collective arrangement transforms, neither fully continuous nor discretely different. Perhaps the most beautiful paradox these new instruments reveal is how something can be simultaneously destroyed and preserved. Our galaxy's identity will dissolve into something new. Yet every star, including our Sun, continues its journey within the transformed system. Astronomical advances also reveal what might be called the paradox of significance. How events of almost unimaginable scale can matter to briefly lived beings on a small planet. The answer lies in consciousness itself, in our capacity to comprehend processes beyond our physical scale, to find meaning in understanding rather than direct experience. This paradox of meaning across scale finds resolution in the continuity of matter. The atoms in your body will continue their journey through this cosmic transformation, participating in processes your consciousness can contemplate but not witness. New studies in astrobiology suggest another intriguing possibility, that galactic collisions might actually increase the total habitable volume within a galaxy. By triggering new star and planet formation, the merged Milkomeda might host more potentially life-supporting environments than either predecessor. A cosmic renewal with implications for life's future possibilities. A creative rather than destructive outcome. This perspective transforms our understanding of cosmic collisions, from catastrophic events to generative processes, from endings to beginnings. A profound shift in how we conceptualize change itself. Chapter 10. The Big Reveal. We've journeyed across time and space through scientific evidence and cosmic speculation. Now we arrive at our central question. What truly happens when the Milky Way collides with Andromeda? The answer emerges not as a single event, but as a process, to cosmic transformation unfolding across billions of years, with distinct phases, each revealing different aspects of galactic evolution. The first phase begins approximately 4 billion years from now, as Andromeda's gravity begins distorting the Milky Way's outer regions, and our galaxy exerts similar influence on our approaching neighbor. These initial distortions will appear as subtle stretching in the outer stellar distributions, stars being pulled slightly ahead of or behind their expected positions, the first visible evidence of impending interaction. Next comes the first direct encounter, approximately 4.5 billion years from now, when the leading edges of both galaxies begin passing through one another. This passage won't involve stellar collisions, but gravitational perturbations, stars being pulled into new orbits, the beginnings of tidal tails stretching outward from both galaxies. From any planet in either galaxy, the sky would gradually transform, new stars appearing where none existed before, familiar constellations slowly distorting, a celestial rearrangement unfolding over millions of years. The most profound revelation is that during the initial encounter, the night sky from Earth, if anyone remains to see it, would contain two magnificent spiral arms stretching across the heavens, one from our own galaxy and one from Andromeda, beginning their cosmic embrace. After this first passage, gravitational forces will pull both galaxies back toward each other, beginning an orbital dance that might include several approaches and retreats, each interaction more disruptive than the last. During these passes, vast bridges of stars will form between the galaxies, tidal tails extending hundreds of thousands of light years, creating spectacular structures visible from vast distances. Gas clouds compressed during these interactions will birth new stars, lighting these bridges and tails with the blue glow of young, massive, stellar systems. A cosmic renaissance of creation. Our Sun and its planets will likely be carried into a new orbital trajectory, perhaps closer to the center of the merging system, perhaps farther out into its halo. its fate determined by gravitational interactions too complex to precisely predict. By this time, approximately 5 billion years from now, our Sun will have entered its red giant phase, expanded to perhaps engulf the inner planets. Its temperature and luminosity significantly altered. Earth, if it survives this solar evolution, will have been transformed beyond recognition. Its oceans long since evaporated, its surface unsuitable for life as we know it. Any observers of these cosmic events would need to have evolved beyond humanity's current form, or have migrated to more hospitable worlds. The timescales involved far exceed human evolutionary periods. As the galactic dance continues, the distinct spiral structures will gradually dissolve, stars adopting more randomized orbits. The elegant arms and disks giving way to a more spherical distribution. The collision doesn't destroy stars, but rearranges them like shuffling two decks of cards together. The stars of both galaxies will find new positions in the merged system, their individual journeys continuing within a transformed collective structure. At the centers of both galaxies, supermassive black holes will begin their own gravitational dance, approaching each other as the galaxies merge, eventually forming a binary system at the heart of the new galaxy. These black holes, weighing millions or billions of times the Sun's mass, will orbit each other for perhaps billions of years, before finally merging in an event of extraordinary energy. Their final coalescence will release more energy than all the stars in the observable universe combined, though primarily in gravitational waves rather than light. A cosmic event of almost unimaginable scale. Throughout this process, smaller satellite galaxies will be affected as well, some potentially joining the merger, others perhaps being ejected by gravitational slingshot effects. The large and small Magellanic Clouds currently orbiting the Milky Way might be incorporated into the new galaxy, or sent on new trajectories through intergalactic space. After approximately 6 to 7 billion years from now, the merger will be complete. The result, an elliptical galaxy containing the combined stars of both predecessors. A new cosmic structure astronomers have already named Milkomeda. This merged galaxy will lack the distinctive spiral arms of its predecessors, its stars moving in more random orbits, creating a more spherical or football-shaped distribution. Gas reserves will be largely depleted by this time, consumed in bursts of star formation during the merger, resulting in an older, redder stellar population with fewer new stars forming. The night sky from any surviving world would be transformed. More stars visible in all directions. It's a familiar band of the Milky Way replaced by a more uniform distribution. A completely different celestial landscape. But this transformation represents not an ending, but a new beginning. Milkomeda will continue its cosmic journey, perhaps eventually merging with other members of the local group. The most beautiful revelation is that this entire process, spanning billions of years and involving trillions of stars, will unfold with a kind of cosmic grace and patience that makes even mountain building seem rushed in comparison. This, then, is what happens when the Milky Way collides with Andromeda. Not catastrophic destruction, but cosmic transformation. Not an ending, but an evolution. A chapter in an ongoing story. The process reveals the true nature of galaxies, not as permanent structures, but as temporary arrangements. Collections of stars flowing through space and time. Merging, separating, and reforming across cosmic timescales. This understanding transforms our relationship with permanence itself, revealing that even the most seemingly stable cosmic structures are themselves in constant flux. The collision narrative connects us to timeframes far beyond human experience, yet accessible to human understanding, to bridge between our brief moment and cosmic evolution. It reminds us that we exist within flowing processes rather than fixed structures. That change characterizes the universe at all scales. From quantum fluctuations to galactic transformations, its perspective doesn't diminish human meaning, but expands it. Connecting our brief conscious moment to processes spanning billions of years. our atoms continuing a journey begun in ancient stars. The answer to our central question, then, is both simpler and more profound than it might first appear. When galaxies collide, they transform. When structures meet, they evolve. When paths cross, new journeys begin. As our cosmic journey concludes, we find ourselves in a beautiful paradox. We've contemplated events billions of years in the future, yet return to our present moment with expanded perspective. The collision of galaxies reveals something profound about existence itself. That transformation, rather than permanence, defines our universe. That what appears most stable is simply changing more slowly. This understanding offers both humility and comfort. We're brief participants in cosmic processes spanning billions of years, yet conscious witnesses to a universe gradually revealing its nature. Our atoms forged in ancient stars and gathered temporarily into the form. Reading these words will continue their journey, perhaps one day becoming part of the merged Milkomeda Galaxy, a material continuity transcending individual consciousness. This cosmic perspective doesn't solve our immediate human challenges, but it does place them within a larger context, one that has consoled thinkers across cultures and throughout history. In the peaceful contemplation of distant futures and vast scales, we find a particular kind of tranquility, a perspective that both accepts our brief moment and connects it to something larger. As you drift towards sleep, consider that you're resting within flowing cosmic processes, that even the stars above are in motion, that everything transforms while something essential continues. Perhaps the most beautiful cosmic paradox is that understanding our transience doesn't diminish our significance, but enhances it. For in our brief moment, we've developed the capacity to comprehend timescales far beyond our own. Join us again as we continue exploring the wonders of our universe, one peaceful night at a time.